This will be the first video in a series of videos for my honors chemistry class covering the different types of chemical bonds. As an overview of the unit, we'll talk about ionic bonds, metallic bonds, covalent bonds, and intermolecular forces of attraction, or intermolecular bonds. So, when we just look at ionic bonds, they're obviously between ions. And typically these are ions from a metal, which forms a cation, and a nonmetal that forms an anion. And you notice I have an asterisk here to indicate that just because you have a metal cation and a nonmetal anion, it does not necessarily mean you'll have an ionic bond. And we'll get into the details of that later. But the force of attraction that holds ionic compounds together is an electrostatic charge attraction. It's a fancy way of saying opposites attract. And this is actually the force of attraction that will hold together all of our types of bonds. The only thing that will change is what the opposites are in this opposites attract electrostatic charge attraction. In the case of ionic bonds, it's between a cation from a metal and an anion from a nonmetal. With covalent bonds, we no longer have ions, we have neutral atoms. And it's typically always between nonmetal atoms. And what we get as a result is a molecule. And then instead of neutral nonmetal atoms, if we have neutral metal atoms, then we get a metallic bond. With intermolecular bonds, or intermolecular forces of attraction, these are the attractions between molecules. And once again, when we talk about molecule, we're talking about covalent bonds. So if we think about what holds a molecule of water together, then that is a covalent bond holding together the oxygens and the hydrogens. But what holds one water molecule to another water molecule, that's our intermolecular bond. It's between the molecules. And there's several types of intermolecular bonds, and the type used will depend upon the type of molecule. And we'll get into quite a bit of detail about that later. Alright, so we have to define some terms as we start off here. And our first term that we have talked about previously is valence electrons. And these, quite simply, are electrons in the highest occupied energy level. Sometimes it's called the highest occupied shell. So if we were to look at a question like, how many valence electrons do the following elements have? We just need to look at the periodic table to make these generalizations. We've already gone through the electron configurations, so we could use those as well. So lithium and sodium, they both end in an S1 configuration. They have one valence electron each, and they're in group 1 of the periodic table. For carbon and silicon, that both of those are in group 14 of the periodic table. They end in an S2p2 configuration. Therefore, they have 4 valence electrons. Oxygen and sulfur, group 16, 6 valence electrons. Bromine and iodine, group 17, 7 valence electrons. So it's very straightforward with representative elements, but it gets a little trickier down here. I've listed the first D block elements we'll run into, specifically 3D here, from scandium over there to zinc. Alright, so if we want to figure out how many valence electrons these have, then it might be helpful to look at their electron configurations. So if I write out perhaps the noble gas configuration of some of these elements, then I'm going to start off with argon. It's my noble gas, and then I'll have my 4s2 3d1 for scandium. And then titanium, instead of 3d1, would be 3d2, vanadium 3d3. When we get down to chromium, though, we have to recall that there was an exception. And we have 4s1 3d5 in group 6. So which ones are the actual valence electrons? And valence means highest occupied energy level, and the 4 is actually my highest energy level. When we wrote out the configurations, we wrote our 4s first and our 3d second because we followed the periodic table, and that was more useful to us. But as we discussed at the time, that the 3ds actually do fill first, and the 4s are on the outside. They're the valence. It's the highest energy level. So we see that almost everything in my D block, my transition elements, are going to have 2 valence electrons because of 4s2. But if I run into a chromium or a copper exception, then I'll have 4s1. So chromium and copper have 1 valence electron each. And we can label our periodic table as we need to. So just as a recap, valence electrons, group 1 has 1 valence electron, group 2 has 2 valence electrons. The D block, almost everything has 2 valence electrons besides my chromium and copper exceptions. Group 13 has 3, 14 has 4, 15 has 5, 16 has 6, 17 has 7, and 18 has 8 valence electrons, with the exception of helium, which only has 2. And then sort of a vocabulary term here, core electron just refers to all of our non-valence electrons, and they tend to be not very significant in chemical reactions. Our valence electrons are on the outside, they're the ones that are interacting with other atoms, and they're the ones that are participating in our chemical bonds. All right, if we look at electron dot diagrams, in some sources you'll see them called Lewis dot structures. In comparison to Lewis structures themselves, they're an easy way to represent our valence electrons. And our rule here is that we don't want to pair up our electrons until we need to. So if I was to draw a couple electron dot structures like magnesium or carbon, argon, sulfur, I'm just going to have the same number of dots around that element as there are valence electrons. So magnesium, I need to have 2 dots around there to represent the 2 valence electrons. So make 1 here and 1 here. And once again, I just don't want to pair them up until I need to. Carbon's going to have 4 valence electrons, so I'll put 4 dots around carbon. Argon's going to have 8, so I'll put 8 around argon. Now one thing I want to make a note of that some people do, something like sulfur, is that they'll make the 6 dots look like this, and that is incorrect. When we have pairs of dots together, we want to make sure that we keep them alongside of the atom. So for sulfur, I would want my electrons to look something like this, rather than going off along the side. Alright, on to the octet rule. So the octet rule, obviously referring to 8 for octet, says that when we are forming compounds, atoms tend to achieve a noble gas configuration. So the noble gases all have 8 valence electrons, besides helium, which has 2. So when forming compounds, atoms attempt to obtain 8 valence electrons. But this really should be called the octet suggestion, because it's violated all the time. There's many, many exceptions we'll look at to the octet rule, so it's just some good advice, but it is not followed all the time. So how does something like this apply to cations? Well, cations are positively charged, so atoms will lose electrons in order to achieve a noble gas configuration. If I look at something like magnesium, magnesium has 2 valence electrons, so magnesium will lose those 2 valence electrons to achieve the same configuration as neon, and then it will have 8 valence electrons. Does that mean that magnesium actually became neon when it lost those 2 electrons? And it certainly does not. It means that magnesium has the same electron configuration as neon, but in order to become neon, it would actually have to lose 2 protons, which, as we know, never happens in a chemical reaction. For anions, we're going to gain electrons to achieve that configuration. So if I looked at something like chlorine, chlorine's going to gain 1 electron in order to achieve the configuration of argon. Once again, chlorine doesn't become argon, but it will gain that 1 electron. So when we want to name ions of representative elements, it's quite easy. If we're a cation, it is just the name of the element. And if we're an anion, we're going to add an IDE ending. So, for example, nitrogen ion will become nitride, oxygen ion is oxide, fluorine ion is fluoride, and so on and so forth. So let's practice this with a couple electron configurations. If I want to write the configuration for the magnesium ion, I'm going to start off here by actually writing the configuration of the magnesium atom. Let me zoom out a little bit here, give myself some room. Alright, so for the magnesium atom, we have 1s2, 2s2, 2p6, and 3s2. So in order to have its 8 valence electrons, it's going to lose both of these 3s2 electrons right here. So those will be completely gone, and my remaining electrons in my valence shell are these second energy 8 electrons right there. So the configuration of the magnesium ion would be 1s2, 2s2, 2p6. The same as neon. With number 2, the electron configuration for oxygen. Oxygen is 1s2, 2s2, 2p4. You were not asked for oxide, which would be the ion, but if we were to form an ion, we notice right now we have 4 plus 2, 6 valence electrons, so it would need to gain 2 more to achieve that octet and have the same configuration as neon. So the fluoride ion will also be the same configuration as neon, 1s2, 2s2, 2p6. The lithium ion. So if I look at the lithium atom, it is 1s2, 2s1. And lithium is going to lose this 1 valence electron, and the configuration of the ion will just be 1s2, the same as a noble gas helium. So this is my one time when my noble gas, it doesn't achieve an octet, it achieves 2, but it's the same as a noble gas. And then for nitride, nitride is going to be 1s2, 2s2, 2p6, after nitrogen gains those 3 electrons to be like helium. To be like neon. Alright, so if we look at a transition metal instead, and here I have the configuration for scandium. Unfortunately, the superscripts didn't quite come out when I transfer this document over. But my configuration for scandium, if I look at the noble gas config at least, it's going to end in 4s2, 3d1. So the question becomes, what ion is formed here? I have 2 valence electrons in my 4s, but if it loses this 3d electron, then it will have the noble gas configuration of argon. And the answer is, it's difficult to predict that scandium will form both a +2 ion when it loses these 4s2 electrons and a +3 ion when it achieves a noble gas configuration. So that happens to apply to almost all of our elements in the transition metals in the D block, that it's very difficult to predict what charge they'll form because they'll form more than one possible ion. So I can't ask you, well, what's the charge of the iron ion? Because you would have to see it in a compound to actually know its charge. If you knew that you had FeCl3, then you can determine, well, this iron has to have a charge of 3 because it's paired with 3 of my chloride ions, and each one of those is -1. To make the entire thing neutral, I'll need a +3 on my iron. But I can't ask you about the iron ion in isolation. It depends upon the cation that it has grouped with. It depends on the anion it has grouped with. There are, however, 3 transition metals that we'll talk about that do have constant charges, and we should label these in our periodic table. Zinc and cadmium tend to have a constant charge of +2, and silver will have a constant charge of +1. Alright, this is going to end our first video, and we'll pick up for our second video here, and we'll get into the details of ionic bonding.